Laser beam divergence. This video is for reference and learning. This video presents the main principles of laser beam divergence, which can also be found in a book or on the internet. You may have to stop and start the video in certain areas if you require more time to review. The aim. Researchers such as D. Marble, Flat Earth Perth, and many others have observed laser beams over distances of 9 miles or greater. A common response to attempt to discredit the observations is the word divergence. Yes, just the word divergence, like it meant something. No explanation, no application of the concept, just the word, as if stating it was all that was required. This short video will present the concept of divergence so the term can be understood, which will hopefully prevent its incorrect use. Note: although I used lasers during my research, as they are a tool used in spectrophotometry, I am not an expert in their construction or in the internal workings of lasers. Lasers are sophisticated devices. Only relevant information to cover their use in the long-range observations they are being used for will be covered in this presentation. There are numerous sources, including books and internet pages, that will take the reader through the interesting intricacies of the laser. How does a laser work? There are a number of YouTube videos that present how a laser works. Some of the videos are more in-depth and accurate than others, depending on the level of understanding required. These links will be in the show notes, the description of this video. What is beam divergence? The beam divergence of an electromagnetic beam is an angular measure of the increase in beam diameter or radius with distance from the optical aperture or antenna aperture from which the electromagnetic beam emerges. Most lasers used in pointers and light shows emit beams with a Gaussian profile or distribution. Gaussian distribution, also known as normal distribution, is a bell-shaped curve. This means that these laser beams are brightest in the center and the intensity falls off towards the edges. Why does a laser beam diverge? Below is only a very simplified description of why beam divergence occurs, but is adequate in the context of the observations being done with lasers. An ideal or perfect laser does not exist. An ideal laser would emit light in only one specific direction. Example, 90 degrees relative to the light generating mechanism, so no beam divergence would occur. In real-life lasers, the light is being emitted in a range of directions relative to the light generating mechanism. Due to the size of the light compared to the physical size of the light generating mechanism and lenses, a proportion of the light generated will be able to leave the final lens at a non-90 degree angle, causing a beam to be generated that diverges, or not just travels in one specific direction. How is beam divergence calculated? The beam divergence of a laser beam is a measure for how fast the beam expands outward from the beam waist. Like all electromagnetic beams, lasers are subject to divergence, which is measured in milliradians, emrads, or degrees. The divergence of a laser beam can be calculated if the beam diameter d1 and d2 at two separate distances, such as z1 and z2 along the laser axis, are known. If the increase in beam diameter between 2 points is measured and the distance between the 2 points is also known, then a mathematical calculation can be applied to work out the angle of divergence, which is measured again in milliradians or emrads. Once the angle of divergence is known, the divergence of the beam at any distance can be calculated. An example: a laser has a beam divergence of 1.5 emrad or 0.086 degrees. This means for every 1 meter of travel, the beam diverges by 1.5 millimeters. What is the radius of the beam at 1,000 meters? You can calculate it this way. So make the diameter 3 meters. The beam at 100 meters has a radius from the center of the beam of 1.5 meters and a diameter of 3 meters. A simple plug-in-the-numbers beam divergence calculator can be found at the following URL, which also will be in the show description. Example: 10,000 milliwatt 520 nanometer green laser 303 model. Using the divergence calculator and double-checking the maths using the tan function, at 15,300 meters the beam diameter is 22.95 meters and the radius is 11.48 meters. At 15,300 meters the beam area is 413.74 square meters. Summary: a laser beam diverges. The divergence of a laser beam can be calculated. The radius, diameter, and surface area of the diverged beam can be calculated at a specific distance. In the peer-to-peer observations, a red laser and a green laser were used. The red laser is 650 nanometers. The green laser is 520 nanometers. The diverging beam of the green laser is more visible compared to the red laser for two reasons. 1. The molecules of the air scatter green light more effectively than red light. And 2. The human eye is more sensitive to green light compared to red light. The diverging green laser positioned at Worthing, 15.3 kilometers away, can be clearly seen due to the fact that green light is scattered by the molecules of the atmosphere and because the human eye is most sensitive to green light. What exactly is scattering? If the light of the beam is not traveling directly into the observer's eye, then how can the beam be seen? What exactly is scattering? Some of the green light is reflected in all directions off the air particles. One of the air particles is represented by the blue dot, not to scale. Some of the reflected green light enters the person's eye, and the diverging beam is observed. Note, the light is actually scattered 360 degrees. Decrease in light intensity. As can be seen, the light intensity of the diverging beam decreases with distance from the source and with distance from the central path of the beam. A laser beam diverges, spreads out, as it travels. A number of responses to laser experiments that have been carried out over water in which the intense source of the laser could be seen have been, you can see the laser because of divergence. Next, we shall see how a diverging laser beam will be affected at sea level on a globe model. Note, the mathematical numbers that are presented are the best that can be used in the situation. The fact that the radius of the Earth in the sphere model is 6,371 kilometers, this should limit the overall accuracy of the numbers to the closest 1 meter. Numbers ranging from thousands of kilometers to meters are being used, and this range limits the accuracy. Despite this, the numbers will be used as fairly as possible to represent the concept being presented. Based on the assumption that the Earth is a sphere and has a radius of 6,371 kilometers, the horizon is 3.57 kilometers from the observer. The green line represents the laser beam between the observer and the horizon. The laser beam is traveling horizontal to the sea surface, and the observer's position, angles A, B, and C, will be calculated. An isosceles triangle can be drawn from the center of the Earth to the surface. Here are the degrees of each of the angles. Next, the height of the central laser beam above the horizon, at 3.57 kilometers, will be calculated. Note, the laser itself is 1 meter above tide level, will also need to be taken into account. An isosceles triangle can be drawn from the center of the Earth to the surface. Again, here are the angles in degrees. Next, the triangle involving the laser beam will be calculated. Laser traveling horizontal to tide level from the laser's starting position. It's been exaggerated and rotated to make it clearer to understand. Laser traveling horizontal to tide level from the laser's starting position, you can see 90.016 degrees, exaggerated again and rotated to make it clearer to understand. Now the other angles can be calculated. Now, 3 factors of the triangle are known. The other angles and lengths can be calculated. Side Z and side W. The central beam of the laser will be 1 meter above tide level at the horizon. That is 3.57 kilometers away from the laser. If positioned at tide level, the central beam of the laser will be 1 meter above the tide level at the horizon. That is 3.57 kilometers away from the laser due to the curvature. The laser was actually positioned 1 meter above tide level, so the central beam of the laser will be 2 meters above tide level at the horizon. That is 3.57 kilometers away from the laser. The laser is 1 meter above tide level. At 3.57 kilometers, the central beam of the laser is 1 meter above the tide level. At 3.57 kilometers, the central beam of the laser is in total 2 meters above the tide level. At 3.57 kilometers, the green laser beam has a radius of 2.68 meters. This means that the bottom 0.68 meters of the radius of the diverging beam is cut off by the sea. 25% of the lower radius of the diverging laser is cut off by the sea. .25% of the radius of the diverging laser is cut off by the sea. Area at 5.37 kilometers, 22.5 square meters. Radius at 5.37 kilometers, 2.68 meters. Here's a diagram showing the bottom of the diverging laser beam being cut off as it strikes the sea. At this point, the bottom part of the diverging beam strikes the sea. The bottom part of the diverging beam is no longer present further down the line. Obviously, the observer is never going to be able to see the laser source due to the curvature. When the diverging beam is cut off, the cut off part does not then start to diverge again. Why? Because divergence is caused due to the light generation mechanism and emittance of light from the laser device, not by light simply traveling through the air. Summary. A laser beam will continue to diverge as it travels. At the horizon, the bottom part of the diverging laser beam will be cut off by the sea. The laser beam, when cut off, does not diverge again. Now that we have an understanding of laser beam divergence, this part of the presentation is going to relate the concept to laser observations that have taken place. The peer-to-peer observation was carried out over the sea at a distance of 15 kilometers or 9.5 miles. According to the curve calculator, the intense central source of the laser beam should not have been observed. it obviously was. Could the camera have recorded the diverging part of the green laser beam and not the actual intense central source of the laser beam? This is what many people have suggested happened, although they have supplied no observations, model, or mathematics to support their assertion. This will be examined based on the observations and the curve calculator from metabunk.org. What is the size of the diverged laser beam at 15.3 kilometers or 9.5 miles? At 15,300 meters, the radius of the beam is 11.48 meters. But because the lower beam radius was cut off by the horizon at 3.57 kilometers to just 2 meters, after 15.3 kilometers or 9.5 miles, the lower radius is still 2 meters. According to the curve calculator, the observer, 1 meter above tide level, will not be able to observe the actual intense central source of the laser and will only be able to observe the less intense diverging beam rising at an angle. The diverging beam will be seen to be less intense as it is not being observed directly, but only because scattered light from the diverging beam is being observed by the camera. If the sea exhibited curvature, the observer would only be able to see the less intense diverging beam and not the central intense laser source. Due to curvature, the observer cannot see down the laser beam to the intense source at the end. The line of sight is blocked by the curvature. It would not be possible for an observer 1 meter above tide level, 15.3 kilometers or 9.5 miles away from the laser device, 1 meter above tide level, to view the intense central beam according to the globe Earth model. This is what the mathematics of geometry prove. Summary. If the sea was curved, it would not be possible for an observer 1 meter above tide level to see the intense central beam of a laser 1 meter above tide level at a distance of 15.3 kilometers away. Based on the numbers generated from the curve calculator, the observer would only be able to observe the scattered light from the diverging beam. On the present globe model, it would not be possible to observe the intense source of the laser itself if it were 1 meter above tide level and 15.3 kilometers or 9.5 miles away. Only the scattered light from the diverging beam overhead would be observable, as illustrated by example in the picture above. But the intense source of the laser can be observed. The intense source can be seen with the beam divergence around it. The intense source can be seen with the beam divergence around it. The laser beam is traveling in an upward left direction toward the observer camera. The diverging beam is losing intensity rapidly with distance. The camera is picking up the diverging beam because green light from the beam is scattering off the molecules of the air and entering the camera. The laser beam is traveling in an upward right direction toward the observer camera. The camera is picking up the diverging beam because green light from the beam is scattering off the molecules of the air and entering the camera. The diverging beam is losing intensity rapidly with distance. The intense source can be seen with the beam divergence around it. The laser beam is traveling in an upward left direction toward the observer camera. The camera is picking up the diverging beam because green light from the beam is scattering off the molecules of the air and entering the camera. The diverging beam is losing intensity rapidly with distance. The intent source can be seen with the beam divergence around it. The intent source can be seen with the beam divergence around it. The intent source can be seen with the beam divergence around it. D. Marble's 10-mile Puget Sound laser test, the link will be in the description. The camera is picking up the diverging beam because blue light from the beam is scattering off the molecules of the air and entering the camera. The diverging beam is losing intensity rapidly with distance. The intent source can be seen with the beam divergence around it. Flat Earth Perth's 15-kilometer laser test, Mandurah. Again, the link will be in the description. The diverging beam is losing intensity rapidly with distance. The laser device is being pointed upwards, preventing the intent source of the laser from being observed. The camera is picking up the diverging beam because blue light from the beam is scattering off the molecules of the air and entering the camera. The diverging beam is losing intensity rapidly with distance. The camera is picking up the diverging beam because blue light from the beam is scattering off the molecules of the air and entering the camera. The intent source can be seen with the beam divergence around it. Being able to view the intent source of a laser device over 9+ miles due to divergence of the beam is not possible on the globe Earth model, unless you are a science and maths denier. These observations are only possible at these distances because water does not exhibit the declared supposed curvature. Don't take my word for what is presented here. Do the observations and/or calculations for yourself. Prove it to yourself. Why hasn't anybody that just throws the word divergence out there in an attempt to discredit the conclusions of these observations actually presented a YouTube video on the concept with mathematical calculations? Because the mechanism of divergence and the mathematics would prove them incorrect. If anyone denies this, then simply ask them to present the mechanism and mathematics. A person's actions will tell you everything you need to know.